Hello and welcome to week 3 video number 2 for assembly language csc314 spring semester of 2018. Here we go. So we left off last time with a deeper dive into the executable file, understanding the hexadecimal representations of some of the binary code and learning something about the offsets into the file, the addresses and so forth, and also learning how to use this bless editor and interpret all this stuff that shows up down here on the bottom. So what I want to do today is now bounce back over to looking at number systems again and getting a deeper understanding of binary representations of information and what's really going on with that. So that's what we're going to do today. Or not today, but in this video. For all I know, you're going to watch 5 videos all on the same day when you're catching up. But at any rate, so to do that, what I want to do is look at just a plain text file first and look at it in the hex editor here. So let's just use this somestuff.txt file that I created before. Maybe you created a similar file already when you were following the earlier videos. So let's go ahead and open somestuff.txt in bless, and that gives me another tab here in bless, and so I can look at this file. So it's a very short file, and of course we have the representation of the printable ASCII characters over here. We have the hexadecimal representation of each byte of data, and we have on the left we have the offsets of the first byte on each line here. And I think this is a pretty good arrangement simply because it goes up. It's nice round numbers in base 16. It's going up by 2.0 every time in base 16 on those offsets. So I think I'm going to keep my editor at this width rather than not have a nice round base 16 number. All right, so now let's look at something though. First, let's look at, I'm going to start editing the file. Oh wait, it's not going to let me. Yeah, there it will. Okay, I just have to actually click in there. Oh, it just doesn't let me do. Bless editor doesn't let me enter returns. There's probably a way to do that, but I haven't looked it up. Doesn't really matter. I'm going to go. I'm just going to put a number in here. Let's go with 43,925, and I'll put some spaces around that just to separate it out. So now the first thing I want to make sure everybody understands, and maybe this, for some of you, maybe you've seen this, for others you have perhaps not. I want you to look at the hexadecimal bytes for these characters. 34, 33, 39, 32, 35. Interesting. Interesting that the second digit, the last digit in each of those hex codes, is the same as the decimal digit. That's convenient. It didn't have to be that way. It's kind of nice. But this is really a 3 times 16 is 48 plus 4. That's really a decimal 52. If I click that, like so, we see that it is a 52. And this one is a 51, and this byte is a 57, and so forth, right? Well, that's because what we're looking at over here with these 5 characters, the 43925, those are ASCII characters. Those are symbols, okay? So when you have numbers in text, in plain text, you're not dealing with binary numbers. You're dealing with ASCII codes of symbols. So let's pop over to our notes and let's start filling in what I'm saying to you here. So first we're looking at just ASCII text versus binary integers and making sure everybody understands the difference between those two things. So in ASCII text, numerals are just characters, just like A, B, lowercase a, lowercase b, plus symbol, parenthesis symbol, and so on. Okay, so that's what the numerals are. They're just characters. Characters are just symbols with no numeric meaning. Okay, there's nothing that ties those characters. If we go back over there, there's nothing that ties these characters to their numeric value in any direct way. Okay, the ASCII code for the symbol 4 is 52. Okay, the ASCII code for the symbol 3 is 51. The ASCII code for the symbol 9 is 57. There's nothing that ties these together. Now let me throw in all the numerals in sequence. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's look at the hexadecimal codes for these numbers. So let me just select all that. So we see that 0 is hexadecimal 30 or decimal 48. Look down here at the bottom for the unsigned 8-bit in particular. So that the decimal ASCII code is 48. And again, you should know what the ASCII code is, and you should always be happy to Google up an ASCII code table. So let's do that again now. I think I have another window open with one already, but I don't want to find it. So let's see if this one's any good. No, I don't like that one. Let's try this one. This one's not too bad. Okay, so if we look for the numerals, here we go. See if I can highlight them all without it going wonky. There we go. So we're seeing the decimal value of the ASCII code. We're seeing the hex value of each ASCII code, and we're seeing what characters are represented. So basically the numerals 0, 1, 2, 3, 4 through 9 are represented by codes 48 through 57. Okay, so you could calculate the actual value of the numeral. Like the value of 3 is 3, right? The value that the numeral 3 represents is the number 3. Okay, the symbol 3 represents the number 3, and if you took 51 minus 48, you get 3. And if you took 49 minus 48, you get 1, and so forth. So keeps wanting me, if I click on these, it keeps wanting to pop this thing up, and that's annoying. But so just kind of keep that in mind. Because the ASCII codes are in sequence, you could calculate the individual value of individual symbols in numeric text, okay? Just by taking whatever its ASCII code is and subtracting the ASCII code for 0. The difference between those two tells you the numeric value of that symbol. That's just kind of file that away in the back of your head, okay? And let's just go back over now and look at what we had here. So we're seeing the ASCII codes for all the numerals in sequence 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have this number here that I typed in to the file right there, 43,925. If we want to interpret that as a number, maybe it's somebody's address, I don't know. But if it's supposed to just be a number and not some code for something else, then that's 43,925, right? But the binary underlying that has nothing to do with the number for 43,925. The binary under that represents those individual ASCII characters. It represents symbol 4, symbol 3, symbol 9, symbol 2, symbol 5. Okay, so So when we're looking at numerals in ASCII text, they're just characters. The characters are just symbols with no inherent numeric meaning. Okay? You have to put the numeric meaning onto those symbols. But in particular, the binary codes that is to say, the ASCII codes, of the symbols representing a number in text have no connection to, I should say, no direct connection to the binary representation of the same number. Okay? So you need to get that straight. All right? Text is text, and binary numbers are binary numbers. They're two different animals. There's a way to convert one to the other and the other to the one, but they're not the same thing. Okay? And we'll clarify that a little bit here. Let's go ahead and make a table. Actually, I'm going to start a table over here. I'm going to give it the first row is going to be ASCII symbol. So what was my number? We had a 4, then we had a 3, then we had a, have to go look, 925. Okay. And now I have to click, get back. All right. Then we had a 9, then we had a 2, then we had a 5. All right. So far, so good. And I'm going to zoom in a bit here just so it's easier to read when you're watching. So those are the 5 symbols that make up 43,925 in text. All right. So let me actually add that in text. Now, what are the binary codes there? Well, or let's just say, what are the bytes for those in hex, a decimal? All right, so for that, we know that these are 0x34, x33, OX39, OX32, OX35. What are those bytes in decimal? Okay, well that's 52, 51, 57, 50, yeah, 50, and 53. If I did the math in my head right, those numbers should be correct. All right, so, and finally the bytes in binary. And for those, I'm going to go back over here, and let's see, I want to make sure I have this selected correctly, and then I should be able to just grab, I get 4 of them this way, not all 5 of them, but that's close. And then back over to the notes, and with a little bit of cut and paste, I'll be there. Now I just need the last byte. Let's see, we had, I have 52 here. 52 plus 1 is 53, so let's just add 1 to that binary byte right there. Okay, so these are the binary bytes. Now what I want you to notice is these it takes 5 bytes to represent a 5-digit decimal number up here, right? So now let's figure out what is 43,925 in binary, if we actually represented as a binary number. And now let's take, let's start a new table. That'll work. So let's start with a decimal number, decimal integer specifically. And now let's do 43,925, and let's see what's going to be the fast way to do that conversion. I've written I don't know how many programs as examples in the past, but I don't have any of them handy at the moment to do that for me, but I think we can make the bless editor do the work for us if we're careful. Will it let me enter? No, it probably won't. Tell you what, I'm going to cheat and I'm going to Google up some binary converter, because I don't feel like doing this one in my head. We will look at the algorithms to do that, but that's not the point of what we're doing right now. So let's see. Text to binary, decimal to binary. That's what we want. So 43,925. Doing it the easy way. All right, so here's the binary for that. Okay. Ooh, they give us a TwosCompliment, a signed TwosCompliment version of it. That's actually kind of useful. So let's go, but let's start with this. Oops. There we go. So do that and come back over and get into the bless editor. No, I don't need to be in the bless editor. I want to be in my notes. I want to be in our notes. Okay, here we go. So now, so that integer in binary is this, okay? And then how else do we want to look at this? Let's see. Broken into bytes. All right. Let's just take that same thing and split it into bytes. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's exactly a 2-byte number. That's kind of interesting. So that's handy. Now let's as a 4-byte unsigned integer. And actually, instead of saying broken into bytes, let's say as a 2-byte unsigned integer here, okay? So, well, as a 4-byte unsigned integer, we just need a bunch of leading zeros there. So all I need to do then is copy and paste that stuff down here. And we're good to go. Now, it's actually kind of good that I chose this number after all, because one thing we can't do is do this as a signed integer, and we'll be talking about the difference between signed and unsigned integers in binary. But the main thing I want you to look here is to look at these bytes. First of all we need to represent a number this big, at least as an unsigned integer, is 2 bytes, okay? Whereas up here in the text, we needed these 5 bytes because we're representing each individual character from the ASCII symbol set for those particular digits. But down here, we're just representing the number straight up as a binary number. We're just using the base 2 number system instead of the base 10 number system, okay? So you can very clearly see that I could represent that number as an unsigned int with just 2 bytes right here, but when I want to represent it in text, I need 5 bytes, and the binary codes are completely different and unrelated. These binary codes look nothing like these binary codes. You might actually find a number which accidentally has the same binary codes, but that would be interesting to see if you could find a number whose ASCII codes were the same as its binary code. I'm not sure such a number exists, but any of you who like a puzzle, see if you can find one. See if you can find one that does that. One thing I want to do with these numbers is make them Courier font so everything lines up. There we go. Actually, I don't need to do that. And I think we can slide that over a little bit. Slide that over a little bit. All right. So hopefully it's becoming clear, crystal clear, the distinction between dealing with something as ASCII text and dealing with something as an actual integer in binary. Okay, so when we go to 4 bytes, we just pad 2 bytes of zeros because we only needed 2 bytes for a number of that size. So, but if you're working with 4-byte integers, then you have to have these extra 0 bytes tag along everywhere. All right, so what else do we want to consider here? Well, what if we were representing these as 2-byte or 4-byte signed integers, which is the more common integer type that you probably have worked with in your past programming experience, right? So, wait, why is it not? It's not creating a new row, so it's going to have to do it this way. Table and insert below. There we go. And now let's say as a 2-byte signed integer. Okay. Impossible. This number is too big. All right. How can you tell it's too big? Well, you can tell it's too big because it has a 1 in the highest bit of the number. All right. That highest bit is used to represent positive or negative when you want to represent something as a signed integer. So you always have to have 1 bit that represents positive and negative when you want to do signed integers. And that's always going to be the first bit of the number, which is right there. This number is so large that as an unsigned number, it needs to use that first bit, which means it's too big to be a signed integer and to be represented correctly. Okay? So you cannot represent 43,925 as a 2-byte or a 16-bit signed integer. You can, however, represent it as a 32-bit signed integer. There's plenty of room there. So let's see if it lets me do this. Okay, so as a 4-byte signed integer. Now, so as a 4-byte signed integer, this number is actually going to look exactly the same as it does as an unsigned integer. Thought I did a copy. I guess I didn't. There we go. So this and this are the same. All right. But now let's go ahead and copy this whole table. All right, and let's look at what if we had a negative 43,925. Well, in binary, when we're just writing it for humans to read, I'm just going to put a minus sign in front of that, okay? Because you just say negative same way in either number system. But if we're actually talking about bits inside the computer, you don't have a minus sign. You only have ones and zeros, okay? So here, as a 2-byte unsigned integer, now we have to say it's impossible because unsigned means only 0 or positive. Okay, so we can't represent negative 43,925 as a 2-byte unsigned integer. It doesn't mean anything. What about as a 4-byte unsigned integer? Also impossible for the same reason. We can only have zeros or positive integers as unsigned integers. So what about here? Well, still impossible because it's too big. It's too big of a negative number, okay? Let me say absolute value, right? So the absolute value of that is too big to represent as a 2-byte signed integer. So finally we get to 4-byte signed integer. It's not too big. We can actually represent this with a 4-byte signed integer. Now, what you might say, since I already suggested to you that the first byte, or the first bit of a binary integer represents whether or not it's positive or negative, maybe you think, well, okay, we can just flip this to a 1 to represent negative and we're all done. And all these digits stay the same. And that would seem to be, from a human point of view, that would seem to be the most natural way to represent binary numbers. And you certainly computers could have been designed to do it that way. But it makes the circuitry for doing computations more complicated, and it doesn't need to be that complicated if you use a different way of encoding. And so I'm crossing those out and going to the next line here and putting the correct representation in. We do need a 1 for seems like I lost my Courier font. We need a 1 to represent the negative sign, but actually almost all of these digits flip. We get 1 1 1 1 1 1 1 1 1 1 1 1 1 1 0 1 0 1 0 1 0 0 0 1 1 0 1 0 1. Almost we would say 0, but actually after you flip them all like this, now I have to add 1 back to that. So that last digit flips back from a 0 back to a 1. And this is the correct binary representation of this negative integer up here, which may seem very strange and mysterious. This is specifically the correct 4-byte or 32-bit representation, okay? So now that may seem strange, but we're going to learn what happened there and why it looks like that, okay? But what you can say is that to take a positive number and turn it negative, you flip all the bits and add 1, okay? That's what you do. Positive to negative, you flip all the bits and add 1, and that gets us to something called 2's complement. So, so for unsigned binary integers, it's as we discussed in week 2 video believe it was video 2, right? Yeah, that's when we discussed number systems over here. So we pretty thoroughly beat that horse to death as far as, didn't beat the horse to death, we beat the dead horse. Yeah, beating a dead horse, that's the saying, right? Okay, so at any rate, we talked that one through, all right? Just how to understand plain positive binary integers, and go between the different number systems, hexadecimal, decimal, and so forth. Now, but now when we want to talk about signed binary integers, okay, that's where things get interesting, like I just showed you. Signed binary integers use what's called TwosCompliment encoding. And this is true in nearly all computer architectures for ages and ages. I am not aware of a computer architecture that didn't use TwosCompliment. Maybe, computers that were built with vacuum tubes back in World War II or something maybe didn't use TwosCompliment. But even then, they probably knew about it and used it, because it would be silly not to. But so they use what's called TwosCompliment encoding, which is what gives you this weirdness here. And the way to think about TwosCompliment encoding is to imagine the numbers. Imagine all your numbers, all your integers on a giant clock that doesn't just go from 1 to 12, but it goes from 0 up and then around to the negatives and stuff. And so I want to draw that out, and I don't know if I can do it because I'm on the wrong system, and I'm going to have to try to draw this with a mouse. Let's see. Oh, I know. I'll actually use the shapes. So here's one way to think about TwosCompliment. I'm going to put a circle down here. All right. And let's just use a pen. Well, let's make it a little thicker. All right. There we go. Now, on this circle, I'm going to start putting the integers. I'm going to put on the inside, I guess I'll put them in decimal form. So let's, where's text? I need text. And I think the way I'm going to have to do this is, let's start with 0. And I'm not sure how this is going to look if you look at this on the web. It might not look too great, but if you open it up in the application, it'll look fine. So let's put 0 there. Now let me put 1. It doesn't let me really shrink these text boxes down, unfortunately. So 1 is next. And 2 next. And 3 next, and so on. And now let me just draw some dots. So dot, 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 dot around the circle. Okay. Now right here, actually right before we get opposite the 0, so right about there. Actually, I don't want those marks like that. Let me make a couple little marks here. what we're going to put right here is going to be the maximum value. So what we need to know is what we're working with. Let's go ahead and say we're working with 32 bit. Well, no, let's do 1 byte just because it's smaller. So this example is for 1 byte integers. So 1 byte 8-bit signed integers. This would be, for example, type car from C programming. Okay. And if you did not learn that the car type in C programming was representing 1 byte signed integers, that's what it really is. Car type in C programming is 1 byte signed integer. It is not really a text character. Okay. It is an integer type. All right, so now let's see. Let me add to that then. What is the minimum value? The minimum value of a car in C is negative 128, and the max is positive 127. Okay? Notice that the absolute value from the min and max are different by 1. So right here, where this arrow is pointing, that should be a 127 now. All right. That's where that is. Actually, I think I can live without the arrow. There we go. So we have 127 there, and working our way backwards around the circle, then there's of course 126, and then 125, and somehow my stuff is already out of alignment. I don't know how that happened. What the? Oh, I know what happened. Let me get this text box down here. Yeah, sometimes OneNote does not always quite work the way I wish it would. That's not too bad. All right, so we have 0, 1, 2, 3 going up. We have 127, 126, 125, and let me go ahead and add some dots. So dot, 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 dots going up, dots going down. Somewhere in the middle there, you're going to have 64. So let's go ahead and throw 64 in there. All right. So you've got the numbers counting up along this side. Now, what happens when you go one step further? You should actually, if you've never done it before, you should actually write a C program that just uses a character variable, counts up by ones, and prints the values each time, and see what happens when you add 1 to 127. Okay? But I'm about to show you what's going to happen. It's going to become negative 128. That's what's going to be right there, opposite the 0, and then it's going to keep counting. So I have negative 127, going back around the circle, and negative 126, and give me a bunch of dots. So let's go dot, 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 and coming around we have -3, -2, -1, right? So -3, -2, and I don't have things lined up perfectly here, but I think you get the idea, and -1. So if we put this range of numbers on a circle like this, then we can quickly see how the binary codes are going to work. So let me put on the outside. So what's the binary, 8-bit binary for 0? 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's 0. Let's put that out here. I'm going to add a little lines or something. Then we have 0, 0, 0, 0, 0, 0, 0, 1. That's 1 in 8 bits. Then we have 0, 0, 0, 0, 0, 0, 1, 0. That's 2. And finally we have 0, 0, 0, 0, 0, 0, 1, 1. That's 3. So far, so good. So we can connect these up with some lines here. Why is that line so thick? Had this problem before. Oh, I think I'll just draw my lines manually. They just won't be nice and straight. So there's to 0, there's to 1, there's to 2, there's to 3. Okay, so for 64, what do we have? We have, let's see, 0, 64, 32, 16, 8, 4, 2, 1. Yeah. That's binary for 64. Then for 125, we have 0, 0, 1, 1, 1, 1, 1, 1. Actually, that would be 127, so 120. So I need to take away 2 to get 125, so there we go. So there's 125 in binary. And then I'll make that 126 by 1, 0 there. And then here, I'm going to make 127. Notice 127 is 0, 1, 1, 1, 1, 1, 1, 1. What happens when you add 1 to this in just normal positive binary numbers? 1, 1, 1, 1, 1, 1, 1. That's like 9, 9, 9, 9, 9, 9, 9 in decimal. You add 1, all those 9s flip over to 0, and the next digit over flips up by 1. So adding 1 to this is going to go to 1, 0, 0, 0, 0, 0, right? Well, that's exactly what happens if you add 1, like in a C program. If you added 1 to 127 as a char variable, it would become the next number on this wheel, -128. So -128 is 1, 0, 0, 0, 0, 0, 0, 0. That's the 1-byte representation of -128. Okay? And then -127, you keep, because you're going clockwise around this circle, you keep adding. So that's going to be 1, 0, 0, 0, 0, 0, 0, 1. And -126 is 1, 0, 0, 0, 0, 0, 1, 0. And you keep going around the circle. Once you get up to -1, well, -1 is when you add 1 to it, that's going to have to flip everything over to zeros, which tells us that -1 is going to be all 1s. So now, as a positive number, that would be 255, but as a negative number, it's 11111111. It's a negative 1. So we have that there. And then we have to subtract, thinking of this as a positive number, we have to subtract 1 to get what it would be as negative 2. So now I can do some copy and paste. A couple things to work with. So there's negative 2, and there's negative... There's negative 3. So now if we just looked at these as positive numbers on the outside, we could also say right here, like that is 255 just as a positive number, and 254 here, and 253 here, and down here we have 128. Oh wait, what did I do? Oh dang it, my things got moved again somehow. Ah, that drives me nuts. I think it's mainly this circle that got moved, so let me adjust my circle back where I wanted it. There, that's better. I think when I put these text boxes in, sometimes it pushes other things around. That's what gets my stuff dislocated. There, that's not too bad though. So we have negative 128 and so forth, but so negative 128 has the same binary coding as positive 128 and so forth. So at any rate, let me put this text down at the bottom here, where it's not going to displace anything. And so yeah, so this diagram hopefully kind of makes clear what's going on. Now I think putting these positive numbers out here might be a little bit confusing. So I'm going to take them back out, unless I added more stuff to explain why I was putting them in there. But just keep in mind that as an unsigned number, 11111111, that is a 255, as we saw over here. So if we're looking at decimal from 000 to 256, binary goes from 0000. At 255 we have 11111, and then at 256 we have 1000000, right? So what we could do is basically kind of take this table and show side by side the signed and unsigned version, where the binary doesn't change, but how we interpret it as a signed or unsigned integer changes. In fact, maybe I'll just grab these two columns and add them over here to this page. Or actually, I think I'll make a new page, and we will put that table here. Alright, did I not copy? Let's try that again. Control-C, Control-V. There we go. And now, so this is unsigned. Oops. And we'll go ahead and make a column for signed integer here. And everything stays the same up into somewhere in this range. And actually, we don't even want to have this row because right now we're just looking at 8-bit. All right. So let me go ahead and delete that row. So 8-bit binary, okay. Now then all we have to do is fix these interpretations. Now we know what 255 is. That's -1. And 254 is -2. 253 is -3. -4. And working backwards into the middle here, actually everything here is positive, isn't it? From that table. So we might as well do this entire column over here. But let's go ahead and flesh this out a little bit. We'll say 125, 126, 127, and this is where it flips over. -128, -127, -126, -125, and then we can flesh out this stuff. So -127. Let's see. That's, well, I mean, positive 127. That's 0111, 1111. Then this is 1, 0, 0, 0, 0, 0, 0, 0. This is 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, and 1, 0, 0, 0, 0, 0, 1, 1. And then we would have to keep going. So I need another row there. And it wants to turn my 3 dots into tiny little 3 dots, but I think we'll just have to accept that. And just to flesh this out a little bit more, 0, 1, 1, 1, 1, 1, 1, 0, and 0, 1, 1, 1, 1, 1, 0, 1, and so forth. But on this side, it's the same 3 numbers there, followed by 128, 129, 130, 131, and so on. Okay, so hopefully this kind of gives you an idea of the way TwosCompliment works. I'm not going to try to explain why it's called TwosCompliment, but that is the technical name for this way of encoding signed integers. And so this is specifically for 8-bit binary integers. All right. If we went to 16-bit, how would that change things? Well, if we look at the circle, that just means we have a lot more numbers on the circle. But you still figure out what the maximum 16-bit number is, and then it rolls over to the maximum negative number and then starts counting down where the positive interpretation of the binary keeps counting up. Same thing with 32-bit. So whatever number of bits or bytes you are using to represent your integers, that just makes this circle bigger. Okay, but half the circle counting up is positive, and then you keep going around counting down is negative. But if you look at the binary representation and think of it as a positive number, it just always counts up all the way around the circle until it gets back to 0. So that way, and the reason it simplifies computer circuitry is that the same circuits that can do addition and subtraction on unsigned numbers can do addition and subtraction on signed numbers, because it actually all works exactly the same way. But you just have to be careful not to increase your sign number past this boundary and flip it over to negative, then your calculations are just going to be wrong. So you have to avoid that situation. But that's it. So hopefully this makes clear how integers, at least, are represented as binary. And again, you've got to make this distinction between ASCII text versus binary, and the way you represent things as bytes. So again, just to come back to that original point, ASCII text for a number, the binary, each byte is just coding one digit out of a decimal number. Usually it's decimal. You could also encode hexadecimal numbers as ASCII text and so forth. So this is the actual binary that represents this sequence of ASCII symbols that happen to represent the number 43,925. But if you want to represent that actual number as a binary number in a computer so that you can do arithmetic and things like that with it, then it has to be represented as a binary number. And typically you're going to use a 2-byte or a 4-byte word. So here, as a 4-byte unsigned integer, it's represented this way. As a 4-byte signed integer, it's represented this way. But that led us to thinking about, well, what about the negative version of that thing and having the first bit represent whether or not you have a plus or minus sign. So the presence of the minus sign is basically represented by the first bit here. But then we have this strange 2's complement representation of integers. All right, so now that's probably more than you ever wanted to know about 2's complement and how binary integers are represented in a computer. But now that you know, you can never unknow it, right? You might forget it, but you can't unknow it. Important distinction there. All right, so that's it for this video. Ran a little longer than I intended, but hopefully I covered it thoroughly for you so that all of this stuff makes sense. And we'll be getting back to actually writing assembly programs very soon and learning more directly how to do things in assembly language. But this is laying a foundation so that you kind of really understand what's going on, which you're going to need to know these things when you start writing your program. So kind of had to get this out of the way at the beginning, and hopefully it makes sense to you. If these things are not making sense to you, you should be emailing me questions. Okay, so I look forward to those emails, and until the next video, I'm signing off.